Let us solve some exact differential equations now. We have seen the proof of necessary and sufficient condition of a differential equation to be exact. While proving the sufficient part of that theorem, we have actually constructed a function which is solution of the given differential equation, which is exact differential equation. So based on that construction, we will derive or we will describe the algorithm of solving an exact differential equation first. There is one formula which is written or which is available in many books for solving the exact differential equation, and the formula is the solution of exact differential equation fxy is nothing but integration of m dx plus integration of terms in n not containing x with respect to y plus constant of integration. But in this video, I will tell you don't use this formula, and why I will explain that with examples, with the help of some examples. So don't use such a formula. You have to use algorithm of solving differential equations only to solve exact differential equation. But there is one shortcut of that algorithm if the differential equation is of that type, etc., etc. I will explain that also with the help of these examples. So we will solve these examples. First we will see what is the algorithm of solving exact differential equation. So we start with let dx plus dy equal to 0 be an exact differential equation. Since it is exact, there exists a function f of xy such that f by x is m, f by y is n, and fxy equal to c is the required solution of given exact differential equation. Now as per our proof, this f is nothing but, since f by x is m, to find f, we integrate this m with respect to x. Since we are integrating with respect to x, any function of y can be treated as a constant. So my f is integration of m dx plus g of y. If you have still some doubt that why this term g of y is there, I recommend you to revisit the video on proof of necessary and sufficient condition of an exact differential equation. So you will get why this term g of y is here. Now, to write this or to evaluate up to this step, we have already used that f by x is equal to n. So to find g of y, now we are going to use this condition that fy is equal to n or f by y is equal to n. So differentiate this f with respect to y. f by y is equal to f by y of this integration m dx plus g dash of y. And if we equate that f by y equal to n, we get actually g dash y is equal to n minus f by y of this integration of m dx. This should be function of y only. And we have proved that since the given equation is exact, that exactness gives us guarantee that this RHS is function of y only. Now, while solving the problem, if you get some term containing x here at RHS, which is g dash of y, that means you must have done something wrong in earlier stages. So, in that sense, it is a self-correcting algorithm. So, this is the crucial step. Now, if you are getting g dash of y as some function of y, just integrate it to get g of y. And then putting g of y in equation 2, you will get your function which is solution of the differential equation. So f of xyc is equal to the required solution. So that is the algorithm. Now let me explain all the steps with help of one example. So this is our example 1. Solve this differential equation. Though we know that we are solving exact differential equations here in this video, but as a procedure, we follow that procedure. We will first show that the differential equation is exact. So, comparing it with m dx plus n dy equal to 0, my m is y square e raised to xy square plus 4x cube, and my n is 2xy e raised to xy square minus 3y square. Now to show that the differential equation is exact, we have to calculate dA by m by dA by y. This 4x cube is not a function of y, so its derivative with respect to y is 0. But for the first term, there is product of two functions of y, and so we have to use product rule. So dA by m by dA by y is e raised to xy square as it is into derivative of y square, which is 2y, plus y square as it is. Derivative of exponential function is the function itself into derivative of the index. That partial derivative of xy square with respect to y is 2xy. So this is dA by m by dA by y. After simplifying it, we get it is 2y e raised to xy square plus 2xy cube e raised to xy square. Now we will find dA by n by dA by x. In dA by n by dA by x, again derivative of this minus 3y square is obviously 0. But here also it is a product of two functions of x. So using product rule, first we write 2y e raised to xy square as it is into derivative of x is 1 plus 2xy as it is into derivative of e raised to xy square is e raised to xy square into y square, and after simplification we will get the same term 2y e raised to xy square plus 2xy cube e raised to xy square. Since dA by m by dA by y is equal to dA by n by dA by x, the given differential equation is exact. Therefore, there exists a function f of xy such that dA by f by dA by x is m and dA by f by dA by y is n. Therefore, f is, now integrate this first function m with respect to x plus g of y. Now, while integrating this, we are keeping y as constant. So, y square is constant. So, it is just 3 e raised to 3x etc. So, its integration is e raised to 3x. So, integration of first term is y square as a constant outside, and integration of e raised to xy square is e raised to xy square divided by y square. Integration of 4x cube is x raised to 4 plus g of y as it is. Simplifying it, we get it is e raised to xy square plus x raised to 4 plus g of y. Now, to find this g of y, we are going to use this equation fy is equal to n. So, differentiate this f now with respect to y. And this dA by f by dA by y or fy is e raised to xy square into 2xy plus g dash of y. That is fy is 2xy e raised to xy square plus g dash of y. Equate it with n. This is n. So, if we equate this with n, we get 2x e raised to xy square plus g dash of y is equal to this. So, this term will get cancelled with this term, and we are getting g dash of y is equal to minus 3y square, and which is perfectly okay. That means whatever we have done so far must be correct. So, integrating it, g of y is minus y cube plus c dash. So, my f is e raised to xy square plus x raised to 4 minus y cube plus c dash. So, either you write that this is equal to 0 is your required solution, or shift that c dash at RHS and write like this, that e raised to xy square plus x raised to 4 minus y cube equal to c is our required solution of given differential equation. Now, you can just observe that this is our required solution of given differential equation, and we know that the given differential equation is exact. That means total derivative of this function f of xy, which is at LHS, must be this, which is my mdx plus ndy. Otherwise it will not be exact, isn't it? So, if I find that x raised to 4, its derivative is 4x cube dx. For minus y cube, it is minus 3y square dy, and the total derivative of this function e raised to xy square is its partial derivative with respect to x into dx, which is this y square e raised to xy square dx, plus its partial derivative with respect to y, that is 2xy e raised to xy square into dy is equal to 0. That means if we group the term accordingly and if we can guess that the group term or group is total derivative of which function, we can directly write the function and then there is no need to write all the steps in this algorithm. So that is the another method or shortcut method, which is this. I am not going to repeat all the things that I have assumed that we have shown already that the differential equation is exact. Therefore, there exists a function such that ∂f by ∂x is m and ∂f by ∂y is n. So my mdx plus ndy or given equation is nothing but ∂f by ∂x into dx plus ∂f by ∂y into dy equal to 0, which is nothing but total derivative of function f. So my df should be this. Now I am grouping the terms accordingly. I am writing y square e raised to xy square dx plus 2xy e raised to xy square dy plus 4x cube dx minus 3y square dy. And now I can guess that the first two terms are nothing but total derivative of e raised to xy square. The third term is derivative of x raised to 4. Last term is derivative of minus y cube. And therefore my function f is equal to e raised to xy square plus x raised to 4 minus y cube. Either equate it with c or write f is equal to these terms plus c, whatever it may be. So this is my general solution. So if you can guess that in the given differential equation, what should be the groups, and for a given group, what is its integration, or in fact for which function the group is a total derivative. If you can guess these things, then there is no need to use there is no need to write all the steps in the algorithm and you can just solve the problem like this. But sometimes the grouping is not possible and terms are very much complicated. We can't do that. And in that case, our algorithm is best because it is applicable to all types of exact differential equations. Okay. Now here, again I can say that this e raised to xy square is because of this integration of y square e raised to xy square with respect to x. X raised to 4 is because of integration of 4x cube. And this minus y cube is because the term here which is in n minus 3y square dy. So what about this term? Since it contains x, that means it is partial derivative of integration of some term here with respect to y. Like here, this term 2xy e raised to xy square dy is because of partial derivative of this term with respect to y, isn't it? So, if any term containing x in n, we can omit that term because we have already considered that term through n. We have already got that integration through n. So we feel that the formula works, and the formula is integration of m dx plus terms in n not containing x. Just integrate those terms with respect to y plus c. So this formula is given in many books, no doubt, but don't use this formula. Not only this formula, but it's another version also. That means integration of n with respect to y plus consider the terms in m which don't contain y and integrate them with respect to x plus c. For both these formulae, don't use these. Why? I will explain with one example, but the basic thing is it is not applicable everywhere. In our previous problem, okay, if we apply it, we get the same answer, no doubt. But in some problem, this formula gives us wrong answers. Basically, no proof of this formula is there. We can't prove it. And we can't apply also it to all the problems. So it's a wrong thing to use this formula. Don't use it at all. So let us consider another example, and then at that example, solving at that example, you will come to know why this formula you should not use. Okay, this is my second example. Solve this differential equation. As usual, we first identify what is m and what is n. Dabba m by dabba y is with respect to y, so it is sin 2x plus 2y. Dabba n by dabba x is equal to with respect to x, so derivative is 2y, and derivative of cos square x is 2 cos x into derivative of cos x, which is minus sin x. As it is, they are not equal, but we know that 2 cos x sin x is nothing but sin 2x, that is a trigonometric identity. So if we use that trigonometric identity, dabba n by dabba x is nothing but 2y plus sin 2x, and then they are equal, and so the differential equation is exact. See one thing here. Normally we have to simplify dabba n by dabba y and dabba n by dabba x. But here the simplification is not algebraic. We are using some specific trigonometric identity to show that they are equal. And in such cases, that formula does not work. How? Let us see. Okay, we solve that problem first with our algorithm and then let us see. So, there exists a function f such that dabba f by dabba x is m, dabba f by dabba y is n. So my f is integration of this m, that is y sin 2x plus y square with respect to dx, and plus g of y. So integration of first term, keeping y constant, integration of sin 2x is minus cos 2x by 2, integration of y square is y square x plus g of y. So to find that g of y, we are going to use that dabba f by dabba y is equal to n. So differentiate this f with respect to y. It is minus cos 2x by 2 plus 2xy plus g dash y, and equate it with n. So we are getting minus cos 2x by 2 plus 2xy plus g dash y equal to n is 2xy minus cos square x. Now 2xy will get cancelled with 2xy. And g dash y is nothing but cos 2x by 2 minus cos square x, which contains terms of x. So, that means we have done something wrong earlier. Or can we simplify it such that these terms containing x will get cancelled? Yes, we can use again the trigonometric identity. That cos square x is 1 plus cos 2x by 2. If we use that, then the term minus cos 2x by 2 will get cancelled. And so this is nothing but minus cos 2x by 2 plus g dash of y is this, and we are getting g dash of y is minus half, which is a constant term and which is perfectly okay. So my g of y is minus y by 2 plus c dash, add that term to my f, and so this is my required solution. Now, if I am going to use the formula says that integrate m with respect to x first, which is minus y cos 2x by 2 plus y square x. And integrate the terms in h which don't contain x. There is no term here which doesn't contain x. That means nothing is there to integrate. Then why this term minus y by 2 is here? Formula gives us answer only this, minus y cos 2x by 2 plus y square x is equal to c. The fact here is I can express cos square x as 1 plus cos 2x by 2. And then one constant term is there which is not a function of x. And then we have to integrate it. Then you may feel that always try that way. But the question is, how can we decide that whether we are going to use any identity or we are going to express such thing here? Because if I express cos square x as 1 minus sin square x, that will be also okay. That is also trigonometric identity. But that gives me another answer, and which is not correct. Then how can we decide that cos square x, keep cos square x as it is, or write it as 1 plus cos 2x by 2, or write it as 1 minus cosine square x? So our algorithm is perfect. It is a proven thing and it gives us correct answer. This formula doesn't work for such problems. And in the same problem, if you notice that while showing that dabba m by dabba y equal to dabba n by dabba x, we have to use trigonometric identity, isn't it? So for such expressions, such functions, basically if trigonometric functions are there, logarithmic functions are there, the formula will not work. And since it is not a proven thing, don't use it. Okay. Now let us see another example. That is our last example. Again, identifying m and n, we are getting m is equal to this and n is equal to this. So we are going to calculate dA by n by dA by x. So here it is, we have to use chain rule, division rule. So we will find the derivative term by term. It is ln of x square plus y square. So first derivative of ln is 1 upon that bracket x square plus y square into derivative of bracket with respect to y, which is 2y. So derivative of ln of x square plus y square, partial derivative with respect to y is this. Plus, here numerator is not a function of y. So there is no need to use division rule. I am taking 2x square outside. Derivative of 1 upon something, 1 upon some bracket is nothing but minus 1 upon square of that bracket into derivative of that bracketed term, which is x square plus y square, is 2y. With respect to y, derivative of x square plus y square is 2y. Now simplifying it, we get this. Now denominators are x square plus y square and x square plus y square bracket square. So if we take LCM, we have to multiply numerator of this fraction by x square plus y square. So by doing that, we get 2x square into y plus 2y cube minus 4x square y divided by in the bracket x square plus y square and bracket square. So which is nothing but 2y cube minus 2x square y divided by x square plus y square bracket square. Now we will calculate dA by n by dA by x. Here there is only one term, but numerator and denominator both are functions of x. So use division rule. X square plus y square as it is into derivative of 2xy is 2y minus 2xy as it is into derivative of denominator is 2x divided by square of the denominator. And if we simplify it, it is 2x square y plus 2y cube minus 4x square y divided by this bracket square, which is the same thing, and therefore dA by n by dA by y and dA by n by dA by x are equal. Since they are equal, the differential equation is exact. So there exists a function f such that dA by f by dA by x is m, dA by f by dA by y is n. So now we are going to integrate this function m with respect to x. But it is not as simple as integrating of this term. Because if you are integrating this with respect to x, if you are going to use substitution, the term 2x should be there, which is derivative of x square plus y square. And it is not simple integrating this term also, because 2x is there, but that additional x is also there. So a lot of simplification and adjustments are required if you want to solve this integration. But then we have choice. You can start with your n. See, these two equations are there. In the algorithm, as stated, we have started with this part, but that is not mandatory. You can start with fy equal to m. That means integrate first n with respect to y. So my f is integration of n with respect to y, which is 2xy upon x square plus y square dy, integration of that. Now since we are integrating with respect to y, we are going to add function of x as a constant, and so this is my first step. So integration of this, now derivative of x square plus y square with respect to y is 2y here. So if I take x outside, it is nothing but at the numerator derivative of denominator is present, and so the integration is ln of denominator. So it is x into ln of x square plus y square plus g of x, that is equation 2. Now we are using this equation. So differentiate this f with respect to x. And so dA by f by dA by x is ln of x square plus y square as it is, derivative of x is 1, plus x as it is, derivative of ln of x square plus y square is 1 upon x square plus y square into 2x plus g dash of x. So after simplifying it, we get it is ln of x square plus y square plus 2x square upon x square plus y square plus g dash of x. So equate it with m and we are getting that g dash of x is 0. So that means g of x is constant. Add that constant to our f and this is my solution. So this is the required solution of given differential equation. So you can choose integrating n with respect to y first also, and that depends on what is your m and n. Okay. So in the exercise, these problems are given to you, answers are also provided. In the last example, you have to integrate first with respect to m and solve the differential equation. And in another method, first integrate this with respect to y and find the solution and check whether your solutions are equal or not. Okay. So solve these problems. If you have any doubt, contact me on this mail ID. Till so far, whatever we have done is, we have seen the specific type or special type of first order differential equations, which are exact differential equations. We have proved one necessary and sufficient condition of a differential equation to be exact. We explored one algorithm for solving exact differential equations, and then we have seen problems based on exact differential equations. So natural question is, what if the given differential equation is not exact? And I think now you must know the answer, because at first video we have seen differential equations in variable separable form. And the question is, what if the differential equation is not in variable separable form? And what is the answer? Reduce it to variable separable form if possible. The same answer is here. If your differential equation is not exact, what is the natural choice? Reduce it. Try to reduce it to exact. And then use our normal algorithm for solving exact differential equations. So to reduce given differential equation to exact, we need some specific terms, and they are known as integrating factors. So in next video, we are going to explore what are the integrating factors and for which differential equations we can find them, etc.